Welcome to this masterclass explainer. We constantly hear terms like El-Nino, La Niña, and the Indian Ocean dipole on the news, usually right before some terrifying prediction of extreme droughts or massive floods. It sounds like a chaotic nightmare, right? But honestly, it's really not. Once you look under the hood, these global climate phenomena operate on incredibly simple, logical rules. And my goal today is to break those rules down so clearly that you'll understand exactly how the gears of our global climate actually turn. Let's dive right in. Here's our syllabus for today. We're going to cover the basics of air pressure, the normal Walker cell, how that cell reverses during El Nino, how it intensifies during La Nina, the Indian Ocean dipole, and finally, how all of this impacts the Indian monsoon. All right, Section 1, the basics of air pressure. Okay, before we can even begin to talk about vast oceans and massive global currents, we absolutely have to understand how air moves. It's the foundation of everything. To make this super intuitive, I want you to imagine two buckets connected by a pipe at the bottom. One bucket is totally full of water and the other is almost empty. What happens? Well, the water naturally flows from the higher potential, the full bucket, to the lower potential. Wind acts exactly the same way. It's literally just the atmosphere trying to balance itself out. It will always flow from an area of high pressure to an area of low pressure. And this brings us to the absolute golden rule of our class today. When air cools down, it gets heavy, right? So it descends to the ground. This falling heavy air creates a high pressure zone on the surface. And because the air is falling, clouds just can't form, meaning high pressure equals clear skies and dry deserts. On the flip side, when the Earth's surface heats up, it warms the air right above it. That warm air gets light and rises, basically creating a low-pressure vacuum on the ground. As it rises, it cools off, forms clouds, and creates rain. So just remember, descending air means dry high pressure, and rising air means rainy low pressure. Moving on to Section 2. Let's look at the normal Walker cell. So let's take that golden rule and apply it to a real-world map. Specifically, the massive stretch of the Pacific Ocean between South America and Australia. Right now, there is an invisible atmospheric loop operating that dictates normal weather patterns across half the globe. Scientists call this incredible engine the Walker cell. And just to give you a mind-blowing sense of scale here, this engine helps push so much warm water westward that sea levels near Indonesia are actually about half a meter higher than they are in South America. Wild, right? Let's break down how this Walker cell operates under normal conditions. Near the equator, we have these strong easterly trade winds constantly blowing from South America toward Australia. Think of these winds like a giant broom, sweeping the warm, sun-heated surface water all the way across the ocean to the Australian coast. Now remember our golden rule? All that warm water heats the air above Australia, making it rise. This creates low pressure, cloud formation, and lots of rain for Australia. Meanwhile, back in South America, because all that warm surface water got pushed away, freezing cold water from the deep ocean gets sucked up to replace it. This is the cold Humboldt current. This cold water cools the air above it, making it heavy. The air sinks, creating massive high pressure. And that is exactly why the Peru-Chile coastline and the famous Atacama Desert are so incredibly dry. This beautifully balanced loop is the normal Walker cell. Which brings us to Section 3, reversing the cell, also known as El Nino. Nature isn't always perfectly stable, is it? It can actually be pretty chaotic. So we have to ask ourselves, what happens when this perfectly balanced system breaks down? Everything we just talked about relies on those trade winds pushing water westward. What happens if those mighty winds suddenly just lose their strength? Well, when the winds weaken, a pretty terrifying reversal happens, step by step. First, without that wind to hold it back, that massive pile of warm water near Australia essentially sloshes right back across the Pacific toward South America. Second, because the warm water moved, that cold upwelling in South America completely stops. Third, South America now has the warm water, meaning the air there rises, creating low pressure, while Australia gets left with cooler water and high pressure. And fourth, the ultimate result, the entire Walker cell completely reverses direction. This reversal is what we call El Nino, and it triggers a massive global domino effect. Suddenly, the historically dry Atacama Desert is getting dumped with rain. Australia, which expects rain, gets slammed with high pressure and severe droughts. But why does this matter for India? Well, normally, the air that rises over Australia eventually falls into the Indian Ocean, creating a really strong high pressure zone there. That high pressure acts like a pump, pushing the monsoon winds up into India. But during El Nino, because the air never rises over Australia in the first place, it never falls into the Indian Ocean. The Indian monsoon basically gets starved of its wind momentum, leading to a drastically weakened monsoon. But wait,
There's a really fascinating nuance of timing here. El Nino doesn't automatically guarantee a disastrous drought for India every single time. If El Nino develops early in the year, say around January through March, the Indian Ocean circulation gets disrupted long before the summer monsoon even arrives, which usually results in a really harsh drought. But if El Nino triggers later, like in April, May, or June, those monsoon winds might have already started their journey to India. It's definitely still going to weaken the rainfall, but a total catastrophic drought might just be avoided.
Okay, Section 4, intensifying the cell, or La Niña. Now that we've seen the chaotic reversal of El Nino, let's look at the exact opposite scenario. What happens when the system doesn't break, but instead goes into absolute overdrive? If El Nino is a reversal, La Niña is a massive intensification of the normal pattern. During La Niña, the easterly trade winds don't weaken. They become unusually strong. They push even more warm water to Australia, and they pull up even more freezing cold water in South America. The high pressure over the Atacama gets even stronger, and the low pressure over Australia gets even deeper. It's basically the Walker cell on steroids.
For students of Indian geography and agriculture, La Niña is absolutely the best-case scenario. Because the air rising over Australia is so intensely powerful, a massive amount of it drops right into the Indian Ocean. This builds an incredibly strong high-pressure zone in the water, acting like a giant compressed spring that eventually unleashes a massive tailwind of moisture directly into the Indian subcontinent. Long story short, La Niña significantly boosts the monsoon rainfall. All right, moving to Section 5, the Indian Ocean Dipole. Okay, we've mastered the Pacific, but there's a whole other phenomenon happening right in India's backyard. This is the Indian Ocean Dipole, or IOD. Now, dipole simply means two poles. The Indian Ocean essentially has its own localized seesaw of water temperatures, with one side near India and Africa and the other near Australia. It works on incredibly simple logic. If the ocean near India is warmer than normal, that's a positive IOD. Warm water means rising air, low pressure, and rain falling over India, a massive boost for the monsoon. But if the water near India is cooler than normal, we call that a negative IOD. Cold water creates sinking air, high pressure, and dry conditions, while the warm water and the rain shift all the way over to Australia instead. And here is a beautiful piece of physical geography to explain exactly how that positive IOD delivers the goods. When there's a low-pressure zone near India due to a positive IOD, the winds naturally rush in to fill it. But as they rush north across the equator, this amazing physics phenomenon called the Coriolis force kicks in. The rotation of the Earth literally acts as a steering wheel, turning those winds sharply to the right in the northern hemisphere. This means those moisture-heavy winds are steered directly and perfectly right across the Indian landmass. Finally, Section 6, the combined impact on Indian monsoons. Let's put all these building blocks together. You understand El Nino, you understand the IOD. So consider this your final exam for this explainer. What happens when these global giants cross paths in the exact same year? Let's look at scenario 1. We have an El Nino, which we know is trying to ruin the Indian monsoon. But at the same time, we have a positive IOD, which is actively trying to boost it. What happens? Well, they fight each other. The result is usually a weakened monsoon, but a catastrophic, severe drought is generally avoided because the positive IOD helps soften the blow. But look at scenario 2. What if an El Nino pairs up with a negative IOD? Both systems are simultaneously starving India of moisture and generating dry, high pressure. When these two align, it is a guaranteed recipe for extreme, debilitating drought conditions across the subcontinent. Now, you might be wondering about that first scenario. Why doesn't a positive IOD completely cancel out El Nino and just give us normal rainfall? The reality is that the Pacific Ocean is vastly larger than the Indian Ocean. El Nino is simply the stronger, more dominant atmospheric heavyweight on this climate seesaw. Even a really strong positive IOD can only do so much against the sheer force of a fully reversed Walker cell. At the end of the day, El Nino will always have the final say on the net impact. We've mastered the mechanics of these ocean currents today, from the basic water buckets of air pressure all the way to complex global domino effects. But as we wrap up, a pretty lingering, vital question remains. As the planet warms, will these extreme reversals, like those devastating El Niños, stop being occasional anomalies? Are we looking at a future where these chaotic disruptions become the permanent new normal for the billions of people relying on the monsoon? It's definitely a sobering thought to leave you with, but hey, understanding the mechanics is the absolute first step to facing whatever comes next. Thank you for joining me on this explainer, and I hope you never look at a weather map the same way again.